All right, college chemistry. Today we're going to talk about electrons, light, and energy and kind of how this all connects to each other. And so let me show you some concepts here. All right, so first things first, when we think about light, you look up at the light maybe in the room you're in or in just wherever you are looking up in the sky. Don't stare at the sun. But the light, when it comes at you, our eyes are not able to see the different colors in that. In fact, we need something, we need a tool like a prism to actually be able to see that the light coming out of most of what we see is actually a mixture of colors. And they have very specific colors. Like if you put light through a prism, you can actually see the different colors that it splits into. And so the red, orange, yellow, green, blue, indigo, and violet, a lot of times we call that Roy G. Biv. Um, those are the different colors of light. Um, our eyes don't do that. And so we have to have a prism, or we're going to use some diffraction grading in class to kind of show you this. But each color of light corresponds to a very specific wavelength and frequency. Okay. And we're going to do some kind of problems with this, but you should be already familiar when you think about wavelength. Then it makes sense if we were to measure the length of a wave, you just pick 2 points on the wave that are exactly the same points. So I could pick the top of the wave, the crest of the wave here to here. That is the wavelength. Here's our symbol. It's called lambda. It kind of looks like an upside down Y. That's our wavelength symbol. Okay. I could have very well picked, I could have picked this point where the wave crosses the axis here. And I could have picked a corresponding point over here. And if I were to measure the distance from there to there, it's the same. So that is our wavelength. And again, you're going to have shorter waves, longer waves, and so on. The other term to talk about here is frequency. Okay. Frequency, which gets the symbol nu, which kind of looks like a cursive V. So if you end up just writing a V instead of a new symbol, that's fine. In physics, you'll end up using F for frequency. I'm okay with that also. But wavelength, try to stick with that little symbol there for lambda. But what frequency means is the number of waves that pass through a point per second. So if you were standing and watching waves come past you, if you could count how many waves per second, that's actually what the frequency is. So the more waves pass that point per second, the higher the frequency. Less waves pass, the lower the frequency. The units for frequency are going to be per seconds. A lot of times we'll see it written as slash seconds or s to the -1. That means 1 over seconds, right? Or really the unit commonly we talk about is hertz. So like radio frequencies, you'll talk about it in megahertz and so on. The units we'll deal with wavelength typically is meters. However, a lot of times the waves we're going to be talking about are in nanometers, and nanometers are really small. So we'll have to do some conversions with that, but kind of keep that in mind. Okay. Now, all of the waves we're going to talk about here are considered to be electromagnetic waves, and we'll fit into the electromagnetic spectrum. I'll show you that here in a little bit. All of these waves travel at the speed of light. So the speed of all these waves are the same, but what can change is the frequency and wavelength. Okay. Now, let me go ahead and show you some equations and constants, and I'm going to kind of work through a couple problems that we want you to be comfortable with. First of all, the speed of light is 3.00 times 10 to the 8th meters per second. So that's pretty fast. 3 times 10 to the 8th, right? So if I were to kind of write that out without scientific notation, well, that's 1, 2, 3, let's see, 1, 2, 3, 4, 5, 6, 7, right? Is that right? So if I move my decimal from here, 1, 2, 3, 4, 5, 6, 7, ooh, I need one more zero there. And that, if we were to put some commas in there, That's pretty big, right? That's how many meters per second that light travels. So we're thinking here that's, tens, ones, tens, hundreds, thousands. We're up to millions. So 300 million meters per second, right? That's pretty fast. Okay, so that is what we're talking about here of the speed of light. Another value that's going to show up here, don't get scared by it, but 6.626 times 10 to the negative 34th power. Holy cow, that's a really small number, right? If you take 6.626, I'm not going to do this, and I move the decimal to the left this time 34 places. So it's going to be a lot of 0 point, with the decimal and then zeros and then the 626. That is called Planck's constant, okay? And why we're going to use these values here is we're going to kind of look at the relationship between wavelength and frequency and how it connects to the speed of light. And then actually, we're going to talk about the energy of these waves. And we have Planck's constant shows up in the equation. The other thing to point out here is we will do a little bit of conversions with nanometers and meters. That will all be given to you. So all this information here, if you need it on a quiz or a test, you'll get those equations and constants. Okay, so first problem we're going to do, what is the frequency of a red light with a wavelength of 675 nanometers? Okay, so we're looking at the relationship between wavelength and frequency. So we're going to use this first equation here. The speed of light is equal to wavelength times frequency. Now, before I can plug in any numbers here, I'm going to have to change these nanometers into meters. So how do I do that? Well, it's 1 times 10 to the 9th nanometers per meter. So I can punch that into a calculator, 675 divided by, and then you can do it however you want. You've got to type in 1 times 10 to the 9th. I'm going to put it in parentheses. I'm going to do 1 times 10 caret 9. You can use your EE button, which is the power of 10 button. That's another thing you can do. So here's what my number tells me, 6.75 times 10 to the negative 7th meters. That is my wavelength in meters, okay? Now, to get frequency, I'm going to take my speed of light divided by my wavelength, and that gives me frequency. See, I'm already just drawing a V because it's a lot easier to do that. So I'm going to take 3.00 times 10 to the 8th meters per second divided by this 6.75 times 10 to the negative 7th meters. Okay, and I'm going to punch this into my calculator. So 3 times 10 to the 8th divided by 6.75 times 10. Let me try this again. I hit the wrong button. 3.00 times 3 times third times the charm, 10 to the 8th, divided by 6.75 times 10 to the negative 7th. And I'm going to get 4.44 times 10 to the 14th. Okay. Now, what does this mean? These are waves per second, right? Or you could put hertz. That's fine. So that's our frequency. Okay. Now, there is a relationship between energy and the different waves that we have. Okay. Very specifically, our relationship, energy is equal to Planck's constant times our frequency. So if we want to know the energy associated with that particular red wave, we're going to take 6.626 times 10 to the negative 34th. The units here are joules times seconds. And then we're going to multiply it by this 4.44 times 10 to the 14th per seconds. Okay. And then we punch this into a calculator. So if you still have your frequency, now multiply by 6.626 and then times 10 to the negative 34th. And voila, you get 2.94 times 10 to the negative 19th joules. If you go back and look at units here, since I have per seconds and I have seconds, the seconds on top cancels with the seconds on bottom, and you end up with joules. Before, I forgot to mention the units for speed of light over the wavelength, back up here in the previous problem, meters does cancel with meters. That's why you end up with this per second. Okay, now on your handout, just a heads up, the handout gives you some energy values at the top of the page. They end up with something that looks a little more like 10 to the negative 21st power. So instead of 2.94, if I multiply that by 100, I get 294, then that would change my power of 10 to the negative 21st. So just a heads up on the handout. That's why you're seeing a little bit different powers of 10 there. Okay, now moving on. Question is, why the heck are we even talking about light and energy in this unit? Okay, it's all about the electron. So the reality is electrons are going to change energy levels. They could go, for instance, from this little diagram here shows, it looks like first energy level to maybe the third energy level. So when that happens, first of all, energy has to be absorbed to get it to go to a higher energy level. So there's a very specific amount of energy or a specific photon of light that needs to hit that electron to get it to jump up to a higher energy level. Okay, and that's going to be different than this one over here, going from maybe the second to third energy level. So different wavelengths of light, different frequencies, and different amounts of energy will change these electrons from one energy level to another. Okay, now as they absorb energy, they jump to a higher energy level. So they jump up when they absorb. Okay. And typically when those electrons get excited and they jump to a higher energy level, they don't stay there very long. And so what ends up happening is they fall back down and they emit light. The light that's emitted has a very specific energy, wavelength, and frequency to it. So that's what we're connecting to here, is this is all about the electron in this unit. And we're talking about the fact that electrons can change energy levels, and we can actually see this happen when light is given off as electrons fall to different energy levels. Okay, so electrons can absorb specific amount of energy, and these corresponding wavelengths and frequencies is something that we actually can observe. Okay, and so here's kind of an example is to kind of show you some corresponding values here. Let's say this is an atom of hydrogen. You've got one proton in the middle. You have first energy level, second energy level, all the way up to 6. And if you look here, here's an example. You've got an electron sitting at the third energy level and it falls back down to the second. As it does that, when it falls down, it gives off energy. What kind of energy does it give off? Well, this from falling from 3 to 2, going from n equals 3 to n equals 2, that's going to give off this red light. And so we visibly could see this in terms of if we were to take a sample of hydrogen, we were to excite it with some electricity, those electrons jump up, and as they fall back down, this specifically, this 3 to 2 energy level fall is going to give off a red light of color, and we're going to be able to see it. Some of the electrons might be falling from fourth energy level down to second energy level. That will be visibly a blue-green light that has a very specific wavelength. So the energy level from 4 down to 2 is going to give us a blue-green light. A bigger jump from 5 to 2, 5 down to 2 actually would give us a violet color. Okay, so the bigger the jump, the more energy that's released, and we're going to see that with different corresponding wavelengths. Okay, this 5 to 2 would have the biggest energy jump. That's going to be releasing the violet color. The smaller energy jump, that actually releases red, which is actually a higher wavelength. So we're trying to make some connections here about wavelength and frequency and energy as it corresponds to electrons changing energy levels. Okay, now let's put this in perspective, big picture. Okay, the electromagnetic spectrum, which you maybe have heard about before, probably middle school science, there are different types of waves. On this end over here, we have radio waves, okay? And right next to that, then we have microwaves. I'm kind of looking at this middle line here. Next to that, we have, after microwaves, we have infrared. Then we have visible light fits in about right here on the diagram. That kind of funnels into that spot. It's kind of blown up so you can see the colors here. Roy, G, Biv, right? So red, orange, yellow, green, blue, indigo, violet, right? And then as you move further to the right, we've got ultraviolet. Hey, that's right next to violet, right? And then X-rays and then gamma rays, okay? Now, a couple things I want to point out on this diagram is the larger waves are on this side. So radio waves are the biggest waves. And if you look at kind of the picture here, it kind of shows from trough or crest to crest from here to here. That's kind of the largest wavelength. If you go down to this other side by gamma, look how close those waves are to each other. I can't even mark that for you to show you the wavelength. So your smallest waves are on this end over here, and the larger waves are on the left end by the radio waves. Okay. Now look at frequency. The smaller the waves, so like gamma waves, they actually have the highest frequency. So big frequency on this side, small frequency on this side, okay? So they are in a inverse relationship. And if you think about in the equation, the speed of light is equal to, no matter what your wavelength times your frequency, it always has to equal speed of light. So if I increase my wavelength, then my frequency has to decrease. Those correspond. They're an inverse relationship, just like with gases. Pressure and volume, remember, was in that inverse relationship. You increase pressure, volume goes down. Same thing here. You have a bigger wave, you're going to have a smaller frequency. You have a smaller wave, you have a bigger frequency. Okay. Now look at the other equation that we have. Energy is equal to H times V. Since these two variables are on opposite sides of the equation, that is a direct relationship. So energy goes up when our frequency goes up. So which of these waves gives us the most energy? This side over here, right? And this over here, just a little bit of energy. So you getting hit by radio waves, not a lot of energy, not that big a deal. You getting hit by gamma rays, absolutely, lots of energy, okay? Now, let's put this in perspective with visible light. Red waves have the largest waves. The violet color has the smallest waves, right? In terms of frequency, red has the lowest frequency and violet has the largest frequency. And then again, energy is bigger on this side compared to the energy on that side. So what we need to remember about all of this is red light has the largest wavelength, the lowest frequency, and the lowest amount of energy in terms of visible light. And on the other end, violet actually has the most energy, although it's the smallest wavelength and it has a higher frequency. So that's something you want to kind of keep in your brain, the connection between wavelength and frequency and energy and how they all connect together. We won't ask you much beyond visible light. Just remember that violet light has the most energy. It has the highest frequency and it's the smallest waves. And then red, on the other hand, larger waves, lower energy, lower frequency. All right.